So I start recording. Okay. So today I will discuss the boost pin type of flexible coupling. Okay. Now I have discussed rigid coupling. Three types of rigid coupling I have discussed in the last class yesterday. So today I will discuss flexible coupling. Now flexible coupling means it will just allow the misalignment. And I have told you what are the types of misalignment, that is axial misalignment, lateral misalignment and angular misalignment. So all these types of misalignment are allowed by flexible coupling. Now we will discuss boost pin type of flexible coupling and another one that I will refer later. Now this boost pin type of flexible coupling is very important and they are mostly used. So it is like the French coupling of the French type of rigid coupling, but there is a difference that some flexible material or some softer material is inserted, is housed in the coupling, so that this softer material is compressed to allow the flexibility. So this is
Sir, one student is trying to enter, sir. Can you please let him enter?
So I have to stop the recording then. Okay, this slide, you are seeing the slide, is it?
Yes, sir. Yes. Yes.
So for boost pin type of coupling, this is the simplest coupling that we use, flexible coupling, and this flexible coupling transmits torque smoothly, and the alignments are, I have already told, that axial, radial and angular, and the amount of misalignment, that is the parallel misalignment, in the range of 0.127 to 0.762 millimeter. The angular misalignment, it can allow plus minus 3 degree, and axial misalignment, it can allow up to 0.762 millimeter. So this amount of misalignment it allows. Okay. Then there are two types of flexible coupling. One flexible coupling is we use some flexible materials that are housed inside the coupling, and they are compressed to allow the misalignment, and also it just absorbs some impact load. So flexible material is used. And in another type of, the second category of coupling, no flexible material is used, rigid materials are used, and these rigid materials allow the flexibility. And I will show you how the rigid materials also allow the flexibility. And here slip coupling will be discussed. Universal joint coupling is also belongs to the second category, but there is no scope of discussing universal coupling, so I will discuss slip coupling. So these are the two categories. Now this is the flexible coupling. Now you see, first of all, I will show you what are the features there in the coupling. On the right hand side, there is a shaft. On the left hand side, there is a shaft. On the right hand side, there is a flange. This is the flange on the right hand side. There is a flange. On the left hand side, there is a flange. And the shafts enter into this side, another shaft enter into this side, and there are keys. There are keys here. Now, the coupling is like this. One student is calling me. Okay. Hello. So recording should be stopped. Otherwise, he cannot be allowed. Okay.
Oh, thank you, sir.
So this is the figure. You just see, this is the figure, and I don't know whether recording is started again. Just let me see. Okay, it has started. So this is one shaft, this is another shaft, this is one flange, this is another flange. Now there is a pin. So there are 6 numbers or 8 numbers or 4 number of pins. Now this area, you just remember the entire figure. That means the 2 flanges are keyed to the shafts, and torque is transmitted through this pin. Say the right hand side is the driver pin and left hand side is the driven pin, and torque is transmitted through this pin. Now I will show you this area in an extended form. Only this area. You see. Now this is the pin. This is the pin. Now diameter of the pin is then step up diameter. So up to this is the diameter of the pin on the left hand side, and on the right hand side the diameter is lower. Okay. Now so pin has 2 diameters. The single pin, there is a step up diameter and the cause behind the step up. Now before that, you see, this is the right hand flange, this is the left hand flange, and there is a clearance. There is a clearance in the range of 5 millimeter or something like that. There is a clearance. Okay. And also you see that these why this step up? Step up because you see on the step up diameter there is surrounding a brass sleeve. That means a hollow cylindrical brass element made of brass that surrounds this step up diameter, and over that there is a rubber bush. So these are rubber or asbestos. These are the soft materials. So higher diameter pin surrounding that brass sleeve, and on the brass sleeve the rubber bush. So rubber bushes are surrounded here, rubber or asbestos, something like that. Now why this step up diameter? The pin transmits the torque. So shear force is generated, and this lower diameter is designed against shear failure. That means due to transmission of torque, a shear stress will be induced, and the pin is made safe. Someone is using the mic. Just mute it. Now this diameter of the pin is made shape against the shear force. Against the shear force. Now, why this step up diameter? The step up diameter because to make the projected area larger. If the diameter is higher, projected area will be larger because there is compression. There is compression, that means the crushing stress will be generated. And since rubber is softer material, then if crushing stress is generated, then the rubber will fail. So if the rubber fails, then the entire purpose of flexible coupling will be lost. Okay, so that is why this area is made larger. Okay, to make the rubber shape. Now, how flexibility is achieved? Now, when there is misalignment, then what happens when there is misalignment between right hand shaft and left hand shaft? So there will be a compression here and rubber is compressed. So rubber becomes compressed. This is one thing. Another thing is you just see the diameter of the left hand side of the pin head. Okay, this diameter is lower than this, so there is a chance of displacement on the axial side. There is clearance and this diameter is lower, so it allows axial displacement like this. Okay, so by compression it allows the lateral displacement or lateral misalignment. By keeping this clearance and making this diameter lower than this, then axial misalignment is allowed. And by when there is a load here, then this pin can be on this side. You see metal to metal contact. On this side there is metal to metal contact, but on this side there is flexible or softer material. So when there is load, then it can act as a cantilever beam. So the pin acts as a cantilever beam. So there is a chance of allowing the angular misalignment. So these are the things which are very important for the flexible boost pin type of flexible coupling. Whether this part is clear or not, you just tell me. Any question about this part of the thing?
Sir,
Tell me.
the pin is subjected to only shear stress or also bending?
Just a minute. Hello? You just continue.
Sir, the pin is subjected to only shear stress or bending stress also?
Pin is subjected to shear stress, bending stress. Pin is subjected to crushing stress also. But since there is higher diameter, so it does not fail against crushing. That means pin does not fail against crushing. Only there is a chance of failure of crushing for bush only. Pin does not fail against crushing. And pin is subjected to shear stress, bending stress, and so there should be a consideration of principal stress.
Okay, sir.
Clear? So,
and sir, one other question. The clearance, how can we calculate the clearance?
Clearance is kept. Just clearance is 5 millimeter. This clearance
you have to consider it in the problem.
You have to consider it because this clearance is for the to allow the bending also, one thing, and also for lateral misalignment. Yeah.
Okay, sir. Okay, sir.
Any question about this? And these these two flanges are made of cast iron, cast steel, or forged steel. Cast iron, cast steel, or forged steel. And since it is made by casting, so this is these have to be tapered. Okay, but in the figure it is not tapered, but this has to be tapered. And one more thing, that means you see this is the threaded part. So threaded part, length of the threaded part should be as minimum as possible. That means from the right hand side, tightening is done. From the left hand side, a cheese is inserted. A cheese is inserted in the slot. A cheese is inserted, and on the right hand side it is tightened. Okay, so thread is there on the right hand side, not on the higher diameter side, on the lower diameter side. And length of the thread should be as minimum as possible, because the pin is there will be stresses. So the lower diameter, that means the core area, length of the core area should be as minimum as possible. This is the question. Is it clear now?
Sir, hello. Sir, can you tell me again about the axial misalignment part?
Axial, you just see. You just see, if this is the thing, what will happen? This left hand flange can be taken to this side.
Yes.
Huh? Is it possible?
Yes.
It can be taken to this side also.
Hmm.
Okay, so the axial misalignment will be allowed.
Oh,
Clear? This diameter is not higher than this outer diameter of the rubber bush. This diameter. Clear? This diameter is lower.
okay, sir.
Okay?
Yes, sir.
Any more question on this part? Okay. So let us continue. Now, this is the simplest and commonest type of coupling. Clear? And it transmits motion from one half of flange to the other half through the bolts. Flanges are fitted with axial clearance, that you have seen, that is fitted to axial clearance. Now on the right hand side, pins are rigidly bolted and loosely fitted on the other side, that is already shown. Now misalignment, parallel misalignment up to 0.5 millimeter, angular misalignment up to plus minus 3 degree, and a beat axial misalignment is in the range of this 0.5 millimeter or 0.6 millimeter. So this type of misalignment it can allow. Okay. Now I have already told the coupling flanges, they are made of cast iron, steel forging or steel casting, and pins are made from normalized steel. Bushes are made of rubber, leather, asbestos or jute. Sleeves around pin are brass. So these are the materials: rubber, leather, asbestos, jute are the flexible material, and sleeve of brass. These are the materials. Now the design aspects. Now looking at the design aspect, more vulnerable is the rubber bush, and rubber bush is designed against bearing force, crushing force. Okay, so the area is more important. Okay, and you will find out that when you will design the bolt against torsion, that means a shear force, then you will see that the diameter will be lower. You will calculate that diameter will be lower. And if you continue this diameter, that means if you make the pin diameter uniform, then there is a chance of failure of rubber bush and the step up of the diameter is needed. Now you see, bearing stress on the rubber bush, I like to find out. Force applied at each pin to transmit the given torsional moment. Say it is F. So F is equal to mt by Z multiplied by R. R is the pitch circle radius and Z is the number of pin. Okay, and there is a empirical relation for finding out Z, that is d by 25 plus 3, while d is in millimeter. So Z you can find out, the PCD, then this F. Okay, so F we can find out, that is F applied at each pin to transmit given torsional moment. Now the outer diameter of the rubber bush. What is the outer diameter of the rubber bush? If it is D1, so diameter of pin plus 2 into thickness of brush slip. You just consider the figure. 2 into thickness of brush slip plus 2 into thickness of rubber bush. Is it clear? The diameter of the rubber bush? Is it clear? Anyone respond?
Yes, sir.
Okay. Then the available rubber bush dimensions are this: 6 to 7.5 millimeter for bores up to 25 millimeter, and for larger bores thickness of 9 millimeter. Thickness of brush slip is 1.5 millimeter. So this is the equation for, this is the simple equation for finding out the diameter of rubber bush. Now projected area. Projected area will be D1 multiplied by just a minute. So this is the projected area. Now L being the length of the bush and P the allowable bearing pressure. Now value of P for the rubber is taken as 0.35 Newton per millimeter square. This is the available rubber quality. So from this equation, length can be, length of the bush L can be determined. Can you hear to me? Can you listen to me?
Yes, sir. Sir.
Okay.
স্যার বলছি যে যখন আপনি স্যার ইকুয়েশন গুলো বোঝাচ্ছেন তখন স্যার সাইড বাই সাইড কি ফিগারটাকে একবার শো করা পসিবল স্যার? তাহলে আমরা মানে ওটার করেসপন্ডিং একবার মানে ডাইমেনশনস গুলোকে একটুখানি মানে ইয়ে করতে পারবো। আচ্ছা, ওকে স্যার, থ্যাংক ইউ।
Okay.
Yes, sir. Yes, thank you.
So this is the projected area. Okay, projected area is clear. So to make bush safe against bearing, diameter of the pin on bush side should be higher. This is the point. This is the point, and you will find out the diameter of the pin also. Then threaded part of the pin. So threaded part of the pin against shear stress. Threaded part of pin against shear stress. So this part is very important. The threaded length of the pin on which the nut is to be tightened. I have already told that should be as short as possible, because the threaded part, there is a core diameter, and this core diameter is vulnerable, very vulnerable, and since there is principal stress, we have to consider principal stress, because there is bending, there is shear. So we should make this threaded length as minimum as possible. This is my point. So shear stress due to the transmitted torsional moment MP on diameter D0 will be, that means D0 is not core diameter. So Fs is equal to F by area of neck. That means F by pi by 4 D0 square. Fs is induced shear stress, and this Fs should be less than the allowable Fs. Fs should be less than the allowable Fs. So up to this clear? Is it clear? This slide? Anyone respond? Hello?
Yes, sir.
So this Fs should be less than allowable Fs. This is induced Fs. This should be less than allowable Fs. Now consider the bending. You look at it is a extended form. This is right hand flange. This is left hand flange, the bounded, and this part is clearance. This part is clearance, and we have considered it as a distributed load. So there is F. Okay, and this is the higher diameter dp. This is d0. Okay, and from here to here it is L, and this is C. From here to here it is L, and this is C. So from here to here it is L minus C. That is that L minus C. It acts as the cantilever beam. So we have considered it as in the form of distributed load. You can consider it in any form. The load distribution you can consider in any form, and accordingly you have to find out the resultant load for finding out the bending moment. Okay, so here it is considered as distributed type of load. So the plane is closely held on the bush half. There is clearance between flanges. Rubber is compressible. This causes cantilever effect, and pin is then subjected to bending. Clear? This part is clear. Is it clear to you? Tell me whether it is clear.
Sir, what is F here?
F is there is a distributed load. So F is that load at the midpoint. That is the resultant load. Okay. And
So,
that
so distance L1 is L/2.
that means from here to here, from here to here distributed load. Okay. So half of this, half of L minus C, half of L minus C. Okay. Half this L minus C. This is L minus C. Half of L minus C. This point. Clear? From here to here, it is L. This is clearance. So it is L minus C. And this is L1. This is the bending arm, L1. Okay. Now let us go to the equation, then it will be clear. The clearance between the flanges is usually 5 to 9 millimeter. Now the load F on the pin is uniformly distributed on the length L minus C. Therefore, the arm under bending moment up to the reduced area is L minus C by 2 plus C. This is L1. L1 is shown. This is L1. This is the bending arm. Clear? This L1 is L minus C by 2 plus C. Clear? So maximum bending moment F multiplied by L1. So induced bending stress will FB will be equal to FL1 divided by pi by 32 d0 cube. Okay. These values should be less than the allowable bending stress, obviously. After calculation of the bending and shear stresses, the pin should be checked against principal bending and shear stresses. And this principal bending and shear stresses is not shown here. That means principal stress is not shown here. So you have to show in your calculation. This is my point. After calculation of the bending and shear stresses, the pin should be checked against principal bending and shear stresses. Okay. and this is not shown here. So in your calculation, in your actual design calculation, this principal bending, principal stresses should be shown. This is my point. Now the initial tightening. So when there will be tightening of the bolt, so on this side you are holding by cheese head, and then by range you have to tighten, and the initial tightening stress should not be very high. This is the point. And for bolt design, we will go for bolt design. This initial tightening stress is very important when we will discuss bolt design. So you just remember now that this initial tightening stress should not be very high, because the threaded part is subjected to so many other stresses. Okay. So empirical dimensions are these. The outer diameter 2D, length of the hub 1.5D, diameter of pin is this. This is the empirical relation. That means 0.5D divided by square root of Z, ECD of pin, thickness of RHS flange thickness. Flange thickness, what is flange thickness? This is flange thickness. This one is flange thickness, this one. This one is the flange thickness. And this one is the thickness of the protecting flange. This is protecting flange and this is flange. So flange thickness means thickness of this, and protecting flange thickness means this one. Okay. So thickness of the RHS flange, and there are two type of thicknesses. Thickness of RHS flange is this, thickness of LHS flange is this, and width of flanges is this. Width of flange means the upper side. That is the width of flanges. Width of flange means this one. This one is the width of flanges. This one is the width of flanges. This one is the width of flanges. So this is the flexible type of boost pin type of flexible coupling. Whether it is clear or not, any question on this is asked. So there is no question.
So PCD of pins মানে?
PCD মানে pitch circle diameter. Pitch circle diameter is this one. This one, this diameter, this D1. This D1 is the pitch circle diameter.
Pitch
Yeah.
circle.
Pitch circle diameter and pitch circle radius. Pitch circle means that is an imaginary circle on which the pins are inserted. Is it clear? Is it clear? Pitch circle.
আচ্ছা আচ্ছা ওকে পিনসটাকে নিয়ে মানে সার্কেল
দেখো এখানে এই সাইড ভিউটা আছে,
সাইড ভিউ থেকে হ্যাঁ
দিস ওয়ান ইজ দ্য পিচ সার্কেল, দিস ওয়ান।
আচ্ছা 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 সেন্টার হ্যাঁ
So any more question? Okay, so I will finish today. I'll finish today because I have a important meeting at 3. So one element is left, that is slip coupling. It will take not much time, but I won't discuss today. So slip coupling, after covering the slip coupling, the chapter on coupling will be covered, and Kamojit requested me to show some numerical problem, and I will try. So when will be the next class? This is my question.
স্যার আপনি বলুন।
Hmm?
Sir, after puja.
After puja means you just